Hello, everyone. Okay, perfect. I think it's the first time that everything is going well on this side. Yeah, it's good. Just gonna do my little round. This is also good. And this is the last one to check. Hope you guys are doing good. I'm doing this live stream now today a bit earlier because our guest is in Europe, I believe. So that was the time that made the most sense. So we're gonna do our best. At least it's morning for me, so I'm usually much sharper in the morning than in the evening. Okay, so this is great. Okay, nice. So I'll show you a bit what we're gonna talk about today. And it's gonna be right here. So today is a fun one. Really looking forward for this one. So, okay, let's put me over here. Good. So what we're gonna chat about today is like a synthetic pre-training data with Joel Niklaus from Hugginface. And like they did a whole bunch of stuff, and this is like still being worked on their side. But like most of the work is already done, published, and there's a lot of information that is there. And this is the kind of work, how to say it, is that like kind of very hard to do, or like as a academic or independent lab, because it requires quite a lot of compute. So like in their case, what's interesting with this paper is that like they've done a whole bunch of ablation. So if you were following like the Nemotron team, like the Playas team, even RC, like they've been working a lot with refining their recipe for synthetic data and for pre-training large language model and post-training also to some extent. So like in their case, they are showing kind of an ablation study on a whole bunch of the parameters that are composing like a synthetic pre-training data pipeline, and they're showing all the result. So we're gonna actually have like a whole lecture on this in a few. Paper is good. You can check it out. It's like 10 page, but it's the paper is a summary of everything that his team have been putting out there. So there's this thing, the synthetic data playbook, which is kind of the long form version of this, which is just over here in true Hugginface fashion. There's This is so fun, man. Everything is you can click on everything. In true Hugginface fashion, you get the end data set, you get the pipeline, you get like the whole playbook, right? So you can download it as a PDF, or you can go over here and learn about it in an interactive fashion. In this very nice blog post, they put a lot of effort in this, a lot of like highly visual data visualization. And Joel, what he's gonna do when he's gonna come in, is gonna give us like the presentation with his commentary on the stuff. And I have a whole bunch of questions also that I can ask him. So it's gonna be pretty fun. If you have any questions, also like don't hesitate to shoot them out. If you're new to this format, basically I invite a researcher. We're gonna have a back and forth. He's gonna teach us something interesting about frontier AI. And then if you have any question, you can just put them in the chat or let me know beforehand, and I'll weave into the discussion. So you can, there's so much information, man. This is so cool. You can check this out. Yeah, so like he's gonna be there in a few about 10 minutes. But before that, right? So like this is like my little sponsored segment, right? But this time, like this is the one thing that is cool with this topic is it directly relevant to RC. The other ones are also directly relevant, but like right now in the paper, you're gonna see like there's literally a part about like synthetic data. The sponsor for this live stream is RC. It's a US-based open lab with like open weight. They show you the whole recipe of how they're doing the stuff, and you can even use like their model, the Trinity large ones, on OpenRouter, on their stuff, on Hermes, like a whole bunch of different providers. Pretty cool model and like very open, so you can get the same kind of DeepSeek feel, but yeah, like in a very, very open fashion. I did an interview with Baron and Lucas a while ago, and I really like their openness and how to say it, how okay they are with sharing like the details about these models. Yeah, and then the cool thing with this is that like in the report that I covered last time, you see here like they're talking about like synthetic data, and they're having the mix that Joel is proposing, which is like not fully synthetic, but like a mix of web and a mix of like non-synthetic data, like actual scraped and processed data, and the synthetic portion where you can do different type of augmentation. And this work for the synthetic, the data mix was done by Datalogy, also a great team, right? So that's that, and I use their model in various ways, right? And like this model, other model, but like it's very good, and it's kind of fast, and it's like you don't need to have like I'd say it like a very complicated setup for what I need, right? Well, how I use these type of model these days is that like whenever I need to prep for an interview, what I like to do is I like to get deep into the actual topic, but I like to cheat a bit by having a lot of context, like even before I go in and I do my stuff. I like to like use them to give me like a background about the interviewee, like a very deep background with like all the other like papers that they've published, like all the other things that they've put out there. I like to have like background on the literature on this specific stream of research. Like this is very useful because then I can make better connection. So like literally this is what I do, and like I take a whole bunch of notes, and then I say like kind of what I want, and this kind of like very simple blurb, right? So I give it the instruction here about like what I need. So like this is like a more of a deep research report that I'm looking for about like the author here and like the content of the interview, and I just let it go, and then it will just like try to do its web search and stuff like that. And after that, when it's done, I'm asking it to generate me a bunch of questions, right? I like to do this to have it generate the research question because I'd said like even the Opus and even the Fable, when I was testing them, they're not that great at crafting question, but they're great at like mapping the space of question type that are interesting, if it make any sense, right? So like they go around and like they're able to kind of cluster the different question. All the questions from LLMs are kind of pretentious in some, like if it makes any sense. Like they're trying to showcase that they know, and it's kind of like gotcha interview question. Maybe I just suck at prompting them, right? But like it's kind of full of like these little kind of gotcha where if it was answering its own question, it could knew the answers. This I don't like these questions because like what's the point, right? Like we're already gonna have like a presentation of the topic, right? Like there's no point in asking about things that you already know. What I like in terms of question is like things kind of behind the knowledge that we have, right? And try to kind of probe in all this different direction. And so what I use them for is like I used it to map like all the different questions that they could ask. I have also my own that are not synthetic, and then I kind of mix some of them and I transform them into like whenever it makes sense. I'll use them for a specific direction. So right now, like I did a whole bunch of how to say it, like digging on like the author, the the literature, the paper, and stuff like that. And usually what I do is I take this and then I edit it a bit, like to kind of remove stuff that are not that useful, right, and that are kind of useless. And then what I do after that is I just ask it, once it's like cleaned up, I just ask it to kind of provide me with questions. So kind of send this like a little instruction, and then it should be good to go, and it will try his best, right, to generate me like about 15 to 20 questions. I try to exhaust the model kind of search space, right? And since it already has like all the stuff in context, or like the report in context, I'm able to kind of go ahead and kind of make enough link in the different section, right? So here, like the different teams that it's talking about, there's like the infrastructure, open science team. Like you see this, it's a bit less interesting for me, so I will usually skip it, or like take some of the element in there. The multilingual and future direction, this is interesting. I took one question from that. The trade-off also, like there was something interesting here, but like was not on the right angle, but like I just nudge it a bit. And like, yeah, quality, diversity, scaling. It's usually not too bad to kind of find like the interesting surface in this. So check it out, check out RC, and big thanks for sponsoring this stuff. And we're gonna go and welcome our host in a few seconds, and we'll be able to look at this and have a whole bunch of cool discussions. So let me invite him here. Okay. Okay, so it should be there in a few. I'm right on time today. Usually I'm struggling with my setup. Try to get a bit better at that. Hello, Joel. How are you?
Hi, Yasin. Good, thanks, and you?
Doing fantastic. Thank you for joining us. Really great. And
Thanks for having me.
yeah, man. Like to be honest, I was I was diving for like a week and a half on all that you guys provided in terms of information about this, and I was like, this is so terrible. Like usually I have a paper to work for, right? And then, like maybe the past literature. But in this case, I had like the paper, the past literature, I had the deck, I had like the playbook, also the blog that is like has these interactive version. It was really great. A lot of the question I had actually got like answered while I was reading more, but I think I found a few that are more on the edge, which I'll be able to ask you today. So thanks a lot for being here. Maybe we can start with a bit of an introduction about yourself and your background in your work. I think that would be good for the community to learn a bit about you, because you have an interesting background, I would say.
Thanks. Yeah, sounds great. Yeah, my name is Joel. I started studying sports science and then switched to computer science in my bachelor's. Then did specialization in data science in the master, and then PhD in NLP. The PhD was focused on legal NLP, like mainly evaluation. The project was about anonymization of people inside Swiss court decisions. And then after the PhD, I worked for Harvey for a year as a research scientist, made a benchmark for translating Swiss legal documents in 5 languages, and worked on improving retrieval systems. And then in August last year, I joined Hugginface, and my first project was the synthetic data playbook. happy
That's
to
a good
talk.
first project. Like this is pretty good. I think what's nice here is that it ties up to a lot of your work that you've done previously, which really cool. You work in you did a PhD, you work in academia and industry. Now you're doing kind of mix of the two with like Hugginface. Um, what's your kind of overall general philosophy with like research problem? I know you've done like benchmark stuff. I know you worked on various different projects. But like when you're tackling a project, a research project that has like kind of this like at the edge of the knowledge quality, what's your philosophy to tackle it?
Yeah, great question. I think similar a bit to how startups operate in general, I would say like if you're tackling a new research project, you don't really know where it's going, what's gonna work and what's not gonna work. In the beginning, you want to explore as many different parts of the problem as fast as possible. For example, in the Fine Phrase project, a big issue was that I had to rephrase like 10 billion tokens just to run one experiment, and that even on the Hugginface cluster, it takes a while. You can't really run that many experiments, right? So you wanna figure out ways to like speed up the iterations as much as possible, and then like try to explore the tree of possible options as broadly as possible, as early as possible, so that you can then narrow in on the ones that sound promising. I did some work on Monte Carlo tree search in my master's, and I feel like maybe be a bit nerdy about that. I would say I would follow like Monte Carlo tree search, where I
Yeah.
first explore, and then when I find like one branch of the tree that looks promising, I exploit until I have like a project that is like well rounded and can be finished.
Yeah, like same thought here. Like because I done like startup stuff for a while, research stuff also, um, and same mental model I have. Like I've done a lot of graph theory things in my research, like for like the project that I've been doing, and my view is that if you can kind of just rephrase and like you rethink about your problem in this way, it's usually much easier to understand like the scale of like what you're trying to accomplish, and like how useful it is to kind of go fast at the beginning, even if like it's a bit messy and you're like but you're just trying to explore a bit the space. But once you have something good that like fit your criteria, like just going over there and getting like juicing up as much as possible is usually like very good, and then you're able to kind of get the good stuff. Okay, cool, nice. I really like that. I also see that like you've done a lot of benchmark, which is funny because I think you're the fourth person interviewing that has a heavy background in making benchmarks. Well, first off, like, can you talk to us about like these different benchmarking work that you've done?
Yeah. So one of the most recent ones that we made was it's called Lexam. So it's legal reasoning evaluation based on law exams from the University of Zurich in Switzerland. And the new thing there was that we really evaluated like long form reasoning, and that was like one of the first works that did that in the legal domain. So like really hard like long form reasoning questions in the law domain. Another one I've touched upon briefly before was called Swiltra Bench, where we benchmark translation models on law translation and head note translation from Swiss court decisions, and then made some before on like general like back in the days in NLP when we looked at named entity recognition tasks or text classification tasks for multilingual legal data sets.
In the ancient time, right? Like the ancient time
Yeah.
of machine learning, right? 2021 or something like that. Hey, this is crazy how like time and the field moved. I had a question that I got from somebody that was collaborating with. It was mainly like on manufacturing data with like their company, and like one thing that they found very hard is trying to get like an internal benchmark for their own stuff, right? Going like, what would you say like is the first few steps? Let's say you have like you're working in a legal business or whatever it is, right? What's the first few steps that you do in order to get started and have like this kind of benchmark set up, like this eval for yourself?
Yeah, I think especially like in the commercial setting, it's very important that the tasks that you look at are like as close as possible to what the system is actually going to do in the end, right? And then diversity is really important. I think these are probably the most like the two things I would focus on first. Like, and then maybe I would probably like yeah, from the academic side, I always have a bias to making the benchmark as hard as possible. Maybe in the commercial side, you have a bit of a different like incentive sometimes to show that your system really performs well. You don't want the hardest tasks in your benchmark. Maybe more for an internal one to see like where still the gaps are and where you can improve. But for the academic side, I think that's the most interesting part, especially now that the methods develop so fast, right? Like, for example, LexSam is almost saturated already, and we only published it a bit over a year ago, so it goes fast.
So you take like 6 months to do it and it's saturated. This is good. Yeah, because also like I work with I am currently working with like a few a client, and like every time we get into like the internal evaluation part, it's always like almost a challenge, because like they never done that in a rigorous fashion that much, and like it's hard for somebody from the outside to kind of like do it for them, because they have the most context, right, about like the problem set and like what they actually want, right? So they kind of have to help like us do it in some way. But this is usually the part that is taking so long. With your work that you're doing right now with the synthetic data pipeline, do you see like a connection and impact for like benchmark making here?
Yeah, interestingly, I've just reviewed a paper for NeurIPS that suggested creating a benchmark as a benchmark task itself, which I found really interesting. Yeah, so basically they measured the LLM's ability of benchmark creation as a task. So that's one interesting side. And then on the legal side, Harvey recently published the legal agent benchmark that was entirely synthetically created.
Okay.
In the legal domain, we always have like when we're talking about public documents like court decisions or legislation, then it's fine, right? We can use those to create benchmarks. But like most tasks that law firms care about, like they use client data, right?
Yeah.
And obviously client data, you cannot publish it. So for that, synthetic data is also a great application, and that's exactly what they did there.
Cool. So it's good. Yeah, so like can I use it as a data augmentation mechanism, or like from the get-go just trying to optimize for like what's it, like a few kind of criterion, and then like the model will build this on that, and you evaluate basically like how close to this criterion it is? Just like the rough idea?
Yeah, so basically they created the whole benchmark is completely synthetically generated. So I think they had like some descriptions of how they want like of what tasks they want to be present in the benchmark, and then they had the models generate like sample documents that would be used as input for the agents to accomplish certain tasks, and then they had like rubrics that are being used to create the agent output in the end.
Okay, this is actually sorry for hijacking the sorry for hijacking my own interview. But like this is actually very interesting for me. Yeah, if you have the paper name, like, do let me know. It's legal agent bench, right? Is this it?
Yeah.
Okay, perfect. So I'll be able to check this out. Yeah,
Legal.
because literally last week I had the same two clients ask me the exact same thing, right? They know kind of what they want to optimize for, right? But they literally just don't have time, right? So it's a bit harder to do, in my view, like with the type of data that we're dealing with, which is like time series data, right? Like text data is much easier to do, but still, in my view, there's ways of using the like a whatever model or agent that you have in order to kind of create the benchmark, at least partially, right? And then you can go in and maybe edit it a bit and stuff, but at least it get the ball rolling here.
Yeah.
Okay, fantastic. Thanks a lot for this information. And I think we can get started with the slide deck, which was really thorough. I'll be asking a bunch of questions like throughout, and if the community has some also, I'll be routing them to you as we go. So you can share your screen.
Sounds great.
Oh wait, actually, we have a question right now. By the way, there's no stupid question. To what degree does using synthetic as distributional shift in model weights, and does that help or harm user performance? I think like this is directly answered in your presentation. Yeah.
Should I go to the presentation then?
Yeah, you can go ahead. It's a great question, by the way, Atta.
Great. Can you see it?
Yep.
Okay, perfect.
I think you can just remove the Riverside pop-up.
This one here?
Yeah, I think so.
Like
Yeah, perfect.
Better now? Great.
Yeah.
Cool. So yeah, I think I've introduced myself already. So yeah, today what we'll cover first, why synthetic data in the first place, right? A bit of a background about pre-training data in 2026. Then how we structured the experiments. So we looked at 3 axes mainly: the prompt, the generator model, and the source data. Then we ran 333 experiments in total to figure out what moves the needle, what leads to good pre-training data. And then we did some analysis to satisfy our curiosity, like why does it work, what issues are there still. Then, as I mentioned already a bit, like running these experiments at scale is kind of expensive. So you want to make sure that you really utilize the GPUs well. And there's a few infrastructure considerations there. And then finally, we ran the final pipeline over 350 billion tokens of FineWeb edu data 4 times for 4 prompts, which created this FinePhrase dataset of 486 billion tokens. So why synthetic data in the first place? Synthetic data is everywhere now. So here we have an example for GLM. But most recent flagship LLMs heavily use synthetic data, like Nemotron 3, Qwen 3, 5.4, RC Trinity, for example. NVIDIA even released a huge synthetic data set called Nemotron CC that we compare against. CAI used synthetic data in mid-training for GLM 4.5, and SmallLM from Hugginface also used synthetic data a lot in post-training. The issue is the recipes are mostly secret. So the frontier labs, they don't tell you how they build their training data, right? They don't know how they filter it, how they construct it, and also obviously not how they use synthetic data. Also not the Chinese labs that are releasing their models open weight. And training data is arguably the most important ingredient in building a world-class LLM, but the recipe is still a black box. So if you can't build the data, you can't build the model, and that's why we're focusing on the data side here. So early on, lots of the compute, or most of the compute, was spent on model training, but now more and more of the compute goes into actually creating or curating training data, and this both in pre-training and in post-training. So in pre-training for generating synthetic data, and in post-training during the rollouts for RL, for example. So you might ask, model collapse, right? Like there is this well-known paper from Shumailov et al. In 2024, where they basically said if you're training on synthetic data, at some point your model collapses. Here we have to be a bit careful because the setup that they used was quite constructed to showcase that you can collapse a model. So they used a closed loop training. They just ran inference on the model and then trained the model on its own output. No human signal in between, like no seed documents. And then the model collapsed. But you would not really do this in practice, right? When you actually create synthetic data in practice, you usually start with a seed document. You like have a strategy of how you want to do it, and you always mix in like real data as well. So in FinePhrase we didn't see any degeneration, and also in the FineWeb paper before that, I think they trained on certain like documents that were already known to be AI generated on the web at that point. So we're still in a phase of alchemy, and we want to turn this alchemy into chemistry and make it a bit more known how this exactly works. And for that we use these three axes: the model, the prompt, and the data. And we do this with like systematic and reproducible experiments. So to give you a bit of the numbers, in the end we did 90 rephrasing configurations, so 90 times we generated synthetic data, and then had 333 evaluate experiments on top of that, where we trained the model and evaluated it on the downstream benchmarks. In total, just for the ablations, this generated 1 trillion plus tokens, just synthetic data. And this used 12.7 GPU years, or 111,000 H100 hours to generate. In the end, we used the final recipe to generate these 486 billion tokens of FinePhrase. So to start with the headline figure, using our data, you can train a 1.7 billion model, either to 31% better benchmark performance, or 3.2 times faster than the best baseline that we compared to at the time. So this is the table prompt, more about that later. And we mixed it at its optimal 70% synthetic ratio, 30% FineWeb Edu high quality data. So we have a little bit of an animation that I had fun generating with Claude. It's not rendering in the presentation, but maybe we can have a look at it later in the blog post. So part 2, what is rephrasing exactly? So the way we see it is you start with a random web document, and then you run it through an LLM to produce variants that change the presentation but keep the meaning intact. So here you can imagine all kinds of different reformulations, right? You could write the tutorial, write FAQs, turn the article into tables and ask questions about it, and so on. So there is a lot of prior work on this, but it was still the alchemy phase. No one really had done a systematic comparison against prompts, across prompts. Nemotron CC, I think they tried like 5 different prompts, which was the most that I can remember. So we look at 3 axes of synthetic data: the prompt, the generator model, and the source data. So for the source data, we have DCLM, FineWeb, high quality data, FineWeb low quality data, and Cosmopedia, another synthetic data set by itself. Then we had 9 different prompt strategies ourselves and compared also against the Nemotron ones and the Rewire ones. And for the model families, we used the best ones that we saw at the 1 billion scale here. And for Gemma, we also scaled up from 270 million to 27 billion parameters to see what difference the size makes.
I just had a question before, just like getting your thought on this, because like I understand that the frontier labs don't want to kind of like reveal like their data stuff, because it's like very like a secret sauce sensitive and stuff like that. And I also understand that like there's the different like open lab that like tried different recipe and stuff, but like rarely they've been doing like an ablation at this thoroughness, right? Why do you think that is? Why do you think that like this experiment now is like possible to run, and before it was not actually done? Like, is it because I don't know, like the it was still like it's in its infancy, like we're still figuring out like what made sense and what didn't make sense, or is it like the compute that is too much? Like, what's your thought here?
I think for the frontier labs, I would not be surprised if they have done similar things internally, right? I just assume they don't publish it. Right. For example, Google, that where I know some people, they just tell me that they can't really publish these things anymore. And OpenAI, Anthropic, they didn't really start in the first place, I guess. And for the academic community, I think there have been some works on this, just that usually, I guess, they don't really have the compute to do it at this scale.
Right. Okay, that makes a lot of sense. And yeah, it does seems like I don't know, I mean, they are talking about some aspect of the modelization, I would say, like the frontier lab and stuff, but the data stuff, it's mostly silent. Like we get some information, true, like I don't know, like Anthropic burning all these books and stuff like that, right? But like it's kind of it's never like a something that is disclosed in such a way. Okay, cool, thank you.
Yeah, sure. Yeah, so how do we do the rephrasing? We have generator models from 270 million to 27 billion parameters. The models from the families I mentioned before. We have different source corpora that we rephrase. So we looked specifically at different quality sets of FineWeb to differentiate whether like low quality data is enough for rephrasing, for example. So we have this edu score classifier that 5 is the highest score and 0 the lowest one. So we have 2 sets of low quality and high quality one. And then DCLM and Cosmopedia. And each experiment rephrases roughly 10 billion tokens and then ablates on a 1.7 billion student and evaluates on 12 benchmarks. We used VLLM for inference, ran speculative decoding because that made sense in the first initial trials that I did. Then we also scored each output by the FineWeb Edu and DCLM quality classifiers to figure out if there is like a proxy that could help us figure out the data quality beforehand, before training the ablation model. And then we distributed this to 100 parallel Slurm tasks, and each of those Slurm tasks runs one VLLM model instance. And this enabled us to like scale up on the cluster like quite well, also allowing other people in the company to use the cluster, right? So just whenever the cluster was free, it would rephrase web data, and whenever someone else used it, it would pause.
Okay, this is good. This is very kind of you.
So yeah, how do we measure success? We just used the ablation methodology from FineWeb because they took a lot of care into making sure that the methodology makes sense at this scale, because there's a few gotchas to be aware of. So at the 1.7 billion scale, for just 20 billion tokens, these models they can't really do a lot. So you wouldn't be able to evaluate them with the normal like multiple choice setup. You would just see random performance at that point, right? So that's why we use the close format. And then we evaluate on 12 benchmarks across 6 categories with 3-shot and a single seed. So general knowledge, reading comprehension, reasoning, natural language understanding, math, and table understanding. So it's quite a broad coverage of the benchmarks that we use. So now to the actual results. First, we'll start with the baselines. So DCLM performed the best on these benchmarks at this 20 billion scale. And then second is the NVIDIA synthetic data set. Rewire is a synthetic data set from Facebook. And then we have more web data set. Interestingly, Cosmopedia and Synth from Playas did not perform very well, just a little bit better than the low quality FineWeb dataset. So from here on, we just compare to DCLM as the best baseline. Then some of these synthetic data sets, they consist actually of multiple different parts generated with different prompts. And they were generated with different models, but just to just compare the prompts, we just used the prompts and regenerated and evaluated on our benchmark so we could compare. So interestingly, for the Nemotron dataset, the performance seems to be mainly carried by this QA pairs prompt, whereas the other ones fall behind. And then there is like the summarize and continuation prompt from a datology paper that were very simple, just continue this web document or summarize it. And the guided rewrite prompt from Rewire is quite complicated. They use the Llama 70B model for that. And yeah, it performs at the baseline level for us here. Then we saw a recurring trade-off, for example, and that like certain data sets perform better on certain benchmarks. For example, DCLM performed well on common sense tasks. And then rephrased data, for example, performed well on knowledge and reading comprehension tasks. So this will come later again.
Yeah.
Sorry, yeah.
And I've seen this like repeated in the paper and stuff. I know that you may not have an answer here, but like just your general intuition, like because I have some ideas, but like I think you have more of a structured understanding of the problem space here. Like why that's it? Why this is? Why like when we like rephrase and change like the synthetically like the structure of the content, we lose kind of this common sense element.
Mm-hmm. Yeah, I'm very curious to hear your ideas as well, because yeah, I don't really have a good explanation for it. maybe for HelloSwag, this is about like continuation of sentences. Maybe the benchmark sentences, they're created by humans, right? And maybe that's just like a different distribution than the LLM generations, and then the model is thrown off. And for the knowledge and reading comprehension ones, maybe this is like a format thing where for Squat, for example, it's like a question answering benchmark, and if we train on FAQs, that may help. But yeah, that's as far as my hypotheses go.
Right. My hypothesis is that like a bit in the distribution element is that like you saw off all of the kind of little noise that the humans are like producing, even like the low quality noise that will be like invariably present in the actual test set. So it doesn't know how to handle these, right? Because it never kind of saw it, because it did kind of like a outside like a sawed off. That's kind of how I'm intuitively looking at it. Which like this could be tested by like taking the rephrased one and like adding back some of this noise synthetically, right? And you could maybe see if like you're able to like get that common sense back. Because if it's really like a noise, I'd say like element, and then like now because you've seen like all these weird edges around the data, it knows like how to not think into too much about that and like go in and answer the task or stuff. Yeah, that's my rough understanding of this, but like I think this is testable. We do have a question by Jan. It says, "What's the value prop behind doing rephrasing? Why do it at all, and what is it trying to do?"
Why do rephrasing and not some other task?
Yeah.
I guess like one of the easy answers is that we have lots of seed documents, right? Like we have basically the whole internet, and if we rephrase it to like a different structure, then we can reuse a lot of the data. Another like early hypothesis or like reason for it was for us was that maybe we can like upcycle lower quality web documents by rephrasing them and like synthetically generating like a higher quality document that still keeps like the overall content. And by starting with like the general like diverse web data, you can keep this diversity, right? Because if you don't start with any seed documents, the model collapse would be more of an issue, I would assume. Like we even see it a bit later with the Quen versus small LM analysis we did, where Quen like generated higher quality math data like problems when you look at it personally, but then it led to lower quality ablation models trained on for the benchmarks. And our hypothesis there is that Quen the Quen's rephrasing leads to less diversity in the output data because it just like is too templatic.
Yeah, that makes I think this is also what like prompted me for this, to think about noise and like little edges that are not there, right? Because like I think like on this part it's a bit different, but still with the small versus the Quen, you see kind of this element, and here on the raw data and then synthetic, you see kind of a similar situation. There's another question by Stem Pondering that says, math is a type of rephrasing, question mark.
Maybe this, to give a bit more context there. Sorry, did I miss?
No, it's good. I think like maybe explaining like the flow from like the document to a math problem will be good.
Yeah. So yeah, basically the idea was just like turning some article about like some like let's assume we have like some Wikipedia article, right? Like similar how you would just ask like questions about it. You could also think of generating some math problems about that article, like grade school math, like some sentence problems you would remember from primary school. Um, there is this like limitation that some articles may just not be suited for math problems, right? And I think that would be like interesting future work, right? Like similar to my colleague did it for fine translations, where he basically had like a gate inside the prompt for the translation. So yeah, a bit of context. He translated all kinds of web documents in all kinds of languages to English, and that can be used to train translation models that go back to these languages in the end. And what he did was he had like in the prompt saying that if this document is like low quality, then don't translate and just like output some flag so they can easily filter it out. And we could do something similar here for the math problems, right? Like if this document is not suitable for math problems, just ignore it.
Cool.
Great. So yeah, here are the 9 prompts that we tried out. So article, like writing an encyclopedic write-up, or an opinionated analysis as a commentary, or a discussion, and so on, right? You can imagine all kinds of different structures that you want to use to rephrase the data. And the 4 ones with the stars were the ones that performed best. So in this case, we use the Gemma 1B model as a default, and we see that the math prompt performs best, and up to the tutorial we see gains compared to the baseline. These are all mixed 50-50 with original data, which is FineWeb Edu high quality data. If we would just do synthetic data by itself, we wouldn't see these gains, but we have another experiment showing that clearly later on. Yeah, so it's more of a restructuring as well, not really like a rephrasing. I think we started a bit with rephrasing, just like a simple prompt, rephrase this. And then we saw that like restructuring actually helps a lot. And like we also see that different prompts help on different benchmarks, right? So then to what extent does the rephrasing model matter? So here we look at the generation size, at the generator size. So from Gemma 3, 207 million to 27 billion parameters. And here I was a bit surprised, to be honest, right? Like you would expect that the 27 billion model generates the best data, and then the 270 million generates the worst, right? For the 270 million, we actually see that, but then we saw that the 1B model like generated at least as good data as the model that was almost 30 times bigger. And I was a bit curious about why that's the case, and to not tell you everything about it yet, but the reason is probably because we measured on a 1.7 billion student model. So if we change the size, we get different results, and they have to be adapted. So then another hypothesis we had was, do we need bigger models for low quality data, right? So we rephrased high quality data and we rephrased low quality data, and then we used different model sizes to do that. And interestingly, as well here, we don't see better results with the bigger models. We also see that the low quality data overall leads to a bit worse performance than the high quality source data, but the difference is not that big. Then, to what extent does the model family matter, right? And here we see that small LM outperforms all the other models, and Quen in this case performed the worst. We think that the reason for that is like a rewrite heavy dataset in the instruction tuning dataset for small LM. Then, to what extent does the model generation matter? Here we see what we would expect. We see from Quen 1.5 to Quen 3 like a clear increase in the performance. So to recap this part, it looks like you can just use a small model for rephrasing in pre-training. You don't really get better data if you use large models. Then small LM is the model family that dominates across prompts. Newer generations of models are better, and the cost matters. So like if you can rephrase with a 1B model, you're like so much faster, right? If you have to use a 27B model for rephrasing. This makes a huge difference in how much data you can rephrase for the same amount of compute.
And I had a question about this part, because at this point, I know you're going to do something different afterward, but at this point you're training like a Quen-like model here, right? And what I understand, the architecture is like closest to, I think, a Quen 2.5 or something like that, like if I remember correctly.
I think Quen 2, yeah, but yeah.
Okay, so like, do you think this is like a form of self-teaching distillation that is going on here, right? For like the formatting of thing, and like from just intuitively, like if the architecture is kind of closer to Quen, I would have assumed that like a Quen model would have been like the best generator for this, but it doesn't seem to be the case. It seems to be like the small one is a bit better on the all front here. So what's your intuition here about that like the closeness between like the generator and like the actual student?
Yeah, it's a good question. I think to me this just makes clear that the data matters more than the architecture, right? I would also assume that I mean, I'm not a specialist on that at all, but I would assume that the architectures of the like small LM, Quen, Llama, and so on are like fairly close, but the data like just makes much more of a like much bigger of a difference during the training as well. But yeah, that's just a hypothesis.
Okay, cool, perfect. I love these. By the way, I'm gonna keep asking like these sort of questions.
Yeah, so next, to what extent do the dataset choices matter? Yeah, here we were interested in seeing whether like synthetic data is enough on its own, right? Like, can we just train on synthetic data in the limit, basically? And here we have quite a clear answer. Synthetic data, like by itself, pretty much always underperforms synthetic data mixed with some original data set. And I think this is like goes together with the thing we've talked about before a bit, that like certain data sets are good for certain tasks, right? And when you can switch, like when you can mix in DCLM, which is good for HelloSwag, then like you will see an increase in HelloSwag, right? And then if you just remove it altogether in the synthetic data only case. So yeah, if you look here, right, like table plus DCLM versus table only, or yeah, so math only, and math DCLM is like the only exception where it's like not better, right? FAQ plus DCLM is better than FAQ only, and so on. There is also other work that did this, and they came to a conclusion that like 30% rephrased and 70% web data gave like the best speed up. For us, it's the other way around almost. So for us, we saw that like around 70%, depending on the prompt, synthetic data like gives us the best results. Yeah, table being the one that outperforms in total.
And this part was very interesting to me. And do you think it's like, because here it could be like multiple reasoning why, right? Like you just need to have like the proper distribution of like the two thing. Like, do you think it's like a proportion thing, or that like the model need to at least see X amount of token that are real, right? And then whatever you add on top will just lead to better performance. Even if it's synthetic, it doesn't matter. Do you think it's more like this, or literally a proportion where, like, let's say, like you have a lot of token for like the real one, but you make so much synthetic data that now it's kind of confused and stuff. So like which part are you aligning more here? On the proportion side, or like a very like a threshold of a capacity for the model?
Yeah, it's a good question. I don't have the Kang et al. Work very present, but one reason for that I could imagine for them arriving at the different rephrased mix is that maybe their rephrased data is not as good as the one we generated, right? Like it takes quite a bit of experimentation to find prompts that work well and versus others that don't, right? Like for example, here the commentary prompt just like worked much worse than the math prompt, right? And it's rephrasing the exact same data, right? Training the exact same model. So the prompt makes a huge difference, right? Like maybe, maybe for different prompts, the synthetic data almost hurts, right? And then you just want to have more real data. Whereas in this case, the synthetic data like pulled the other ones up, right? That could be like one hypothesis, but it's also quite difficult to compare like across benchmark setup and like training configuration, and like I don't know how many tokens they trained for, right? Like it could be a scale issue as well. Like maybe they trained for longer or less long. Could be many things.
Yeah, that's really cool. Can you go back to the previous slide also? Like, because this was also very stark. Like, you have like the commentary that like kind of suck, right? And then you have like the table math stuff that is kind of at the top. Is there any other format, like a wacky format that you've tried? Let's say like, I don't know, like generating what did I say? Like generating like for our HTML website, or even like not just like a HTML website, but just like I don't know, like a XML type of structure over the content, right? Same content, but like an XML structure, or same content in an HTML structure, or like same content but in a kind of discussion format, a la like a how is it, like a forum type of stuff, right? Like a Reddit or Hacker News. Have you explored like different other ways of creating these prompts?
Yeah, so I've tried these 9 once. Just like thinking about how I would rephrase it that like makes sense, right? XML, HTML I didn't try. Usually in pre-training you do the opposite, right? Like you extract the text from the HTML and from the XML. And it's probably also not measured by the benchmarks, like to what extent the model can generate HTML or XML, right? Like in the ones that we measure, right? So there you would probably see no gain for that. If you have like benchmarks that actually measure that, then I guess it would be useful. Another thing we tried like early was just like rephrase in general, right? Like just telling it like make this higher quality. But yeah, that's
just make it better. Make a better data set.
Exactly, yeah. Just try
Um,
harder.
yeah, make no mistakes. There's a Raven that is asking a question. Is there also the order of these data sets being used for pre-training that matter for this distribution? That's actually also very interesting. What's your thought here?
The order. Yeah, I mean, that's like curriculum learning is a whole different field of study, right? Like I'm not an expert, but to the extent of my knowledge, it's quite clear that curriculum learning doesn't really work for pre-training, or like yeah, like there's no clear gains as far as I know. I think it's very important for RL, I've been told,
Yeah,
but
post
not
training,
for
yes.
pre-training.
Yeah, I think it has some quite a lot of gain how you engineer like the ordering of like the different tasks that you're giving, especially for continual learning. Like I've been talking to Aiden and the folks at ETH Zurich, and it seems to have like an impact on it, like especially on the difficulty of the question that you're asking, kind of, right?
Mm,
And like ordering them like properly. But
mm,
also this is a whole other mess. So
mm.
okay, cool.
Yeah, it's a very interesting approach, right? Like I'm also a bit sad that it doesn't work for pre-training, but it's good to see that it works for post-training, that we're not like completely disappointed.
I had a last question about the format, right? Um,
Mhm.
um, do you think that like I don't know if a 1B model is too much for it, but like maybe bigger, like adding multilinguality to the format, right? It's the same thing, right? But like now it's translated in like this other language. I would assume that like the generator then need to be kind of a bit better, let's say, than 1B, right? They need to be kind of. I think that then it will maybe make a difference. But would it be even useful for as a synthetic, how would say, like element for the model that being trained?
Yeah, that's a great question. Yeah, I think like would you do the rephrase like the translation at the same time as the restructuring, or
I, w-
like in a
I
next
would
step?
Yeah, like there's two ways of doing it, right? You either kind of like you have it is the same thing, right? But now it's like a rephrase in the language, so we can keep the same format and stuff like that. Or what you could do is like you have your 9 things, right? Like your 9 different prompt, but then you translate all of these into like another language. Then you have like this bigger augmentation. But I would assume that like it would be better to do the first one, right? You just gain one of it, but you keep kind of the noise and then the particularity around like the actual kind of messier text. Yeah, that's my hunch, but I'm basing it on absolutely nothing.
So basically, just do the translation, right?
Yeah, exactly.
Um, Yeah, I mean, like fine translations did basically this, but from the low resource languages to the high resource languages, to English basically, because we know that language models seem to be similar to humans, that they understand languages they don't know very well, but they can't speak them very well. So they can translate much better from a low resource language to English than the other way around. Um, so, but the like the value of this fine translation data set is mainly for training and translation model, right? If you wanna, if your goal is to like get a data set that can be used to train better multilingual models, then we would need to do it the other way around, right? And that's
Yeah.
exactly, I think, what you're asking for. I think for that it would be a very valuable thing to do. Yes.
My hunch is that like since they understand like these like low resource language, but like they're not that fluent to kind of move in it, right? And they would much prefer have it in, I don't know, English, which they've seen more. My hunch is that like it would just introduce another kind of noise, right? In in the data, but like that still fits what we're trying to like get them to um, get them to output, right? That's kind of
Mm.
my hunch around it, right? Like it will create a bit this more diversity, but for this to be correct, you need to have a good translator. Otherwise, like it will be mostly kind of garbage translation. Yeah. Okay. Cool.
So you're saying it like it might not be that bad, like if the translation is not perfect, right?
I think it will not be that bad. It still need to be kind of coherent in structure, right? So that like the other model can kind of pick up on that, right? Yeah, and I think like there's different type of translation to different type of like if you do this from like English to Arabic, I mean that's gonna be a pretty huge lift for the model. But like language that are kind of adjacent, I would say to English might introduce some of the I don't know like the particularity of a language that like can be captured for the benchmark, and it's not gonna be like too hard of a task. But then you create like this diversity in formatting that we're kind of capturing with the rest of the format. That's my rough intuition here, but like I have no
Yeah.
I have no
I mean, yeah,
basis.
you would. I guess you would need like multilingual benchmarks to measure the gain, right?
Yeah, yeah, maybe.
But yeah, I think that could be a really cool project. Maybe I should consider working on that next. Yeah. So continuing on the dataset choices. Which non-synthetic dataset should you mix in, right? And here we see that basically FineWeb Edu HQ and DCLM, they're like the same basically, it doesn't really matter. And Cosmopedia and FineWeb Edu low quality are worse. And interestingly, there is quite a big lift from just training on FineWeb Edu high quality data to mixing it into like synthetic data. Whereas for DCLM, we don't really see that gain, which I was a bit surprised by. Then here we test what happens if the mix-in is the same as the source. So that means we have the source. We rephrase low quality FineWeb Edu data here, and then we mix in the same data again. And the same for Cosmopedia, DCLM, and high quality, right? And here we see that, yeah, FineWeb Edu high quality and DCLM just clearly beat the rest. So looks like the source does matter. But if we fix to a strong mix-in, I think in this case we fix to FineWeb Edu high quality, then the source data doesn't really matter that much anymore. So and this is a really cool result, I think, because this tells us that like the data wall that we've been hearing about a bit is not really an issue, right? Like you can even take like very low quality data here, like FineWeb Edu low quality is really like the worst of the worst almost for in terms of web data available. Like it's Edu score 0 to 1, right? Like this is really bad. But like if you rephrase this and mix it with high quality data, you can get like almost DCLM level performance, right? Which is a cool result, I feel. So yeah, this opens up a much larger pool of data, right? Because like DCLM, I think they start with an initial pool and then filter it down to like less than 1% of the data that they actually use for pre-training in the end.
Right. And this is very interesting because like I haven't looked at like FineWeb like low quality, but like at this point, what is it that we're generating? Like if it's like this is low quality, it's like is it more of a sort of literally distillation of whatever the generator is, the 1B, and then that's kind of what's going into the model, and then like the edu low quality just doesn't matter anymore. Like is this or like it literally is fixing these data set? Like what's your thought here?
To me, I don't think it's distillation because the rephrasing is being done by a 1B model, right? Like yeah, maybe yeah. Yeah, I mean the 1B model is trained for a long time, yeah, and the student model is like from scratch, yeah. So it could be, I guess, yeah. Yeah, I don't know how would you test that? Which
I don't
one
know,
is
and like if it's distillation, then like a bigger model should get better performance, right? Or maybe
yeah.
the capacity of the model is capped at like 1B and stuff. So this I'm not sure. But then what you could test is just try to lower the quality even more of the data set, right? Like at some point, if you're just feeding it pure garbage, like literal, like you stripped away all
Mm,
information, right? And then you
mm,
shove it through like this model and say like, this is interesting data. You should go ahead and make these like these in different template, and you see what happened. And if it is able to kind of boost the performance, then you could theoretically say that like that portion of the gain from like this literal noise
mm,
data that has a structural language, but like there's nothing in there for sure. We like removed all possible information. This is the portion that is can be attributable to distillation, and this other portion is like the actual like a gain from the data set, and you can have like the data set being varied here. I think that will be a way to test this out.
yeah, yeah, good point. Yeah, that would be interesting. I think there is also work on like literally training on like random stuff, right? Like in pre-training.
Yeah, yeah.
And I think even there they see like um, surprisingly strong models coming out of that.
The models just want to learn, right? You feed it whatever.
Yeah. Yeah, so then I think another natural question is like, to what extent does it help to combine different prompts, right? But here I was a bit surprised about the results. So I would expect like if you combine like all the different data sets, you would get better performance. And we see it to some degree, but like not really clearly, right? Like all the prompts is it's just a little bit better than just using the math prompt together with FineWeb high quality. I think the interesting result here is that the all prompts they can basically almost like replace the source, right? Like if we have lots of different synthetic data with different prompts that are all good, we don't need the high quality source data anymore. Like we're almost at the math level quality here. Another thing, just like a small interesting, like a small experiment I ran out of curiosity was the typos. The rewire paper, the prompt there was full of typos, um, and I was like, does this make a difference if I improve it? If I like fix the typos and the grammar? But interestingly, it turns out to be the opposite way, or like no
Interesting.
difference at all. So for the 1B model, they engineered the typos very well. It looks like.
Oh, this is so cool.
And yeah, so to summarize here, it really looks like prompt design is the most important part. Maybe a bit sad as a result, but that's what it is. The model size, it seems like beyond 1B, it doesn't really help that much. Maybe 4B, but 12B or 27B doesn't improve. Then you should always mix with original data. Don't just train on synthetic data alone. And the source seems secondary if you have like a strong mix in data set. So let's look a bit in more detail how and why this works. So first, we were interested in seeing if rephrasing like
This
leads
is
to
so funny
benchmark.
because like on Twitter, there's a guy that asks the same question. It says like, um, what about benchmark contamination? Have we covered that yet? So we're literally here now.
Yeah, perfect timing. Yeah, so here we ran a 10-gram overlap audit of the benchmarks to the like rephrased corpora, and we just sampled 5 billion tokens for each of the corpora. The reason for that is that depending on the prompt, there is different amounts of tokens being generated. So we always started with 20 billion tokens input data, and then some models, some prompts lead to much more rephrased data than others. And yeah, we see that the like rewire has the most, is like the most contaminated, but still it's like at a low rate. So that's like the number of documents per billion training tokens. And so for example here, like the FineWeb Edu HQ also is contaminated to some degree, right? And the rephrased corpora that we produced are not, they're on average less contaminated. There's just one that is like more. Then another question is like, how much is seed noise? Like we have a data seed and a training seed, like model initialization seed fixed. But what if these seeds are like lucky for some prompts and unlucky for others? So we ran the same recipe across 9 seeds pairs, so like 3 data seeds and 3 model initialization seeds, and across 4 student sizes, and we see that the difference is very small. So just like a gain of 0.05 is like already way above the noise. It depends a bit on the benchmark. So for drop, the noise is much bigger than for HelloSwag, for example. Also, the model initialization seed dominates the noise much more than the data ordering seed. Here we see an overview of all the rephrasing runs plotted across GPU time and the like aggregate macro score on all the benchmarks of the student model trained on the data set. And we see that the Pareto frontier is dominated by the small models. So and yeah, like we don't really see big gains like as we've seen before, right? Like from rephrasing with huge models that generate a lot of data. For example, here like we spent a year of compute for one rephrasing run, and it is worse than spending 1 week with this other model, right?
Oh, this is kind of crazy. Like this is insane, and I think like this has to do with like maybe the limitation of like the 1B that is addressed with like the other experiment that you've done, right?
Yeah, exactly. Yeah. So this ties back a bit to the original question that you asked, like how to do research. And I really wanted this to work, but it didn't, unfortunately. Like the current setup is really time consuming, right? Like you first have to generate like 10 billion tokens. Like as you see here, if you choose the wrong model, it takes you a year of GPU time. And then you need to train a 1.7 billion model on 20 billion tokens, which also like is like takes 3 hours on 8 nodes, so 64 GPUs for 3 hours. That's also quite an investment, right? And only then you still need to evaluate, right? Like it's quite an investment for each run. So it would be great if we could just like have a small proxy, like the quality filters that were used to create the FineWeb Edu or the DCLM pre-training data sets. But unfortunately, it doesn't really work that well for for synthetic data. So the highest correlation with macro averaged scores after the benchmark is the DCLM score difference between the input data and the synthetic data, which is 0.6. Not bad, but still like not great. And the edu score, like if we just look for the output score from the edu classifier, there's like no correlation at all. Interestingly, like for some like if we have a high output edu score, we actually get bad benchmark performance. So like the edu score even seems to be like sometimes negatively correlated with the final benchmark performance, as we can also see here.
Right. We have two very interesting questions. Right. There's one that is asking about. I've noticed that LM have favorite vernacular. Does that vernacular survive rephrasing like Opus, for example, really like load bearing? Do you see like depending on like which of the generator, if like it's using more like the ticks of these models, or or like there's not that much difference at this scale?
Yeah, I haven't noticed that, but yeah, maybe I need to look into the data a bit more.
Yeah. And there's another question that says, do you think that the technique like rephrasing could be contributing toward the model better understanding a true language semantic invariant to the exact word choice?
Sorry, I'm not sure I fully follow the question.
I mean, like I think like a bit similar to my thought about like it's sawing off the edges, right? With like of I don't know, the different typos, like different ways of saying things, and it's like more standardizing. I mean, the language that is being used, and like because there's now different format. Yeah, like do you think like this plays a role about like understanding like what are the great good structure to kind of use to be able to like how to say it, like the good structure of language, right? And then you remove like all of the different kind of ways of doing it, and it's a bit more standardized now. Do you think there it's more like this, or like it's something else that the model is understanding better with the synthetic data?
Yeah, I mean, my worry about the standardization is a bit like the loss of diversity, like
Yes.
similar to the thing we've seen with the Quen model, right? But yeah, like the original hypothesis was that like the web, like original web text can be very noisy and like full of grammar errors or like typos or like OCR errors and stuff, and that we can get rid of those, and like this generates more high quality data that like improves for like pre-training performance. But yeah, I'm not sure about like
Right.
the exact mechanisms behind it. Yeah.
Okay, perfect. Cool.
Yeah, so we also looked a bit at diversity metrics. So can maybe diversity metrics can predict performance. There's different ones like Venn score over sentence embeddings of the outputs. This helps on some benchmarks, but not on others. Like on the aggregate score, it doesn't help. There is gradient diversity, like G-Venn score. And this is the best predictor that we found for reasoning performance. So if we go back here, we see that for reasoning, there's like no really good score, right? But the G-Venn score works well for that one, but then it doesn't work for others. So maybe like if you combine different scores, then you could achieve like a higher than 0.6 correlation. But yeah, I don't know. To me, it seems a bit over-engineered and a bit like overfitted in the end. So yeah. I didn't do that. So yeah, it looks like there really isn't a good proxy that you can use, and you really need to train and evaluate each data set independently, it looks like, unfortunately. Then another thing we saw, like we talked about the 1B generator a lot, right? So one reason for that could be that the student model that we train is just too small, right? Like maybe if you train a 1B model, then it just can't learn from like better data generated by the bigger models, right? And when we look at this, we train student models of different other sizes from 0.5 billion to 6.2 billion on the exact same data mixes. And then we sweep the Gemma 3 generators from 270 million to 27 billion on 3 different prompts. And again, always mix in the FineWeb edu. And what we see here is basically the bigger the student gets, the easier it can differentiate between good and bad data. So for the 1B model, what we saw was that like after the 1B generator, it just basically squashes everything together, right? It just can't differentiate anymore. And same for the 0.5B, right? Like here it can't even distinguish the 1B model from the 270 million model, and the difference between the smallest and the biggest model is just very small, right? But then when we go to the 2.9 billion and the 6.2 billion, we see a much bigger difference, right? And here we actually see like the 12B model performing quite well. So we see that the 207 million model across like all prompts and student sizes is really bad. The 1B model as a generator is quite good already, much better than the 270 million. And then if we train on if we train a bigger student model, then we see that bigger models actually have benefits.
And but for me, this was also super interesting, right? Because like the gain, when you look at the chart, right, the gain with like the bigger generator, at some point you have to do the trade-off with like the compute that you're taking, because like it kind of jumps, right? Do you think that like, because the 270 still is kind of it's kind of doing something, right? It's like not like doing nothing, but do you think that like purpose-built trained 270 million parameters, right? Like that is specifically like a fine-tune or something like that to be a very good generator. Do you think that there will be gain over there to kind of climb up to the, I don't know, the 4B and stuff like that? Because then like you would just need to train and make sure that like whatever prompt that you're using, not for the translation here of like from one data format to another, is well done, right? But then like you have like the gain of like having this very compute efficient model. Like I would assume it's like the perfect task for like a small model, because you have the information and then you have the kind of the output. Like there's very little unknown that you have to work with here. You just have to be able to understand like the different templates. Yeah, what do you think?
For sure, yeah. I think here I just focused on prompt engineering, right? Because the design space was so huge already. But I think this is a very interesting future work. Yeah, like concurrently, an intern at Hugginface did something similar where I think he fine-tuned. I don't recall the results, but yeah, I think this could be like really promising. Yeah, I agree. Like a 270 million model should be able to do this, right? It's not like the task is super hard.
Yeah, maybe there's some template that are harder than others. Let's say the math one, maybe it's like the hardest and stuff, right? But then you can kind of mix and match the different model size, and you don't have to kind of use like the 27B for like just making tables, right? Like, so like maybe there's a trade-off also at like the different difficulties that you can use.
Yeah, for sure. Yeah, so here, yeah, it also just matters a bit like on the prompt, right? Like for the math prompt, we see the 1B model being the best, even with the small student size, right? Also, one thing we saw here in the plots here before, right? Like the student size just makes a huge difference in terms of the macro score on the benchmarks. I mean, this not very surprising, I guess, but still, like after 20 billion tokens, like the difference is quite big. And like the generator size, or like the data, doesn't make that big of a difference. Like you can still scale like a larger model by quite a lot, right? But just having a larger model by itself, you see quite big gains. Then also here we investigated how chatty the models are with different prompts. So overall, the table prompt led to very short outputs, and the FAQ and the tutorial ones led to much more verbose ones, and also the variance across models was much bigger there. Yeah, we also looked a bit at compression ratio versus downstream performance. Very early in the project, I chatted with a friend of mine, and his hypothesis was that synthetic data generation is basically like doing compression, or like because of compression, it leads to better pre-training performance. So like you start with a certain amount of information, say like in 1,000 tokens, and then you rephrase it into 200 tokens, and you still have the same information, or most of it, but now represented in 200 tokens, and since you still train for 20 billion tokens, you have much more information in the synthetic data now than in the original one, right? Like that was his hypothesis. And it's a bit difficult, like with our results now, because like for some we do see that relationship, but then also like it goes in the other direction. We just see like very big variance in the like space where the compression happens. So can't really answer this question, unfortunately. Yeah, I've talked a bit about this already. So like we were a bit surprised when we looked at the results, like the output from Qwen and SmallLM. When you look at the Qwen output, it looks great, but then and when you look at the SmallLM output, it looks weird, and then you see the SmallLM output being much better on the benchmarks. So we tried to figure out why that's the case, and yeah, the hypothesis we arrived at was in the end that the SmallLM just creates much more diverse outputs, and diversity seems to be important for pre-training. So for example, we see that Qwen only has 40 different 10-char openings, whereas SmallLM has like almost 2,000 ones, right? Then we also looked a bit at the math output. So for example, SmallLM has like in 23% of cases, there's no numbers in the math rephrase data. Whereas for Qwen, it's just 0.1%, right? Like we see that Qwen follows the instructions much better than SmallLM. We also checked the accuracy of the equations, and so more accurate equations for Qwen, and like more valid math overall, but still for pre-training, this doesn't seem to matter. Like for pre-training at this stage, it's probably just not about correctness, but yeah, more about diversity.
And these results hold for like small and like Qwen as the model grows in size here?
Sorry, how do I change?
Yeah, for the student, like if the student is bigger, let's say it's a 6 or like whatever, Does this still hold that like the diversity of the small one, like doing whatever, is
That's
better than
a
Quen just following the instruction?
that's a good question. That I don't know. I haven't run that experiment.
Yeah,
Yeah.
because like the for me like this is the dumbing down with the numbers. I think almost make me think that like the problems are now more in like the capacity of the 1B model to kind of understand, like more in the like, I'm thinking more of a in from a post-training curriculum learning lens here, where like the problems are easier and then like you can just kind of like figure it out better than like just Quen being this kind of distilled kind of god model that like knows much better than like this poor 1B trained from scratch, right? And it's like just putting numbers everywhere and like I don't understand numbers yet, right? That's like the rough feeling I had when I saw these results. But it doesn't explain the diversity of like messed up information, right? Maybe it's like it's adding enough noise with like simple enough structure and output that like it can pick it up and like kind of remove the noise and say like, yeah, this is what matters for me now. Versus the other one is like kind of a ruthless teacher in some way, where like no, it's this is the thing that you need to understand. It's clean. It's this is it, but it doesn't have enough diversity to kind of figure out like the hardness of it, like, and it just doesn't get it right. While the other kind of climb up a bit, and then like yeah, even if the teacher is messy, the problems are kind of more in the ballpark of this poor train from scratch 1B.
Yeah, that's a good explanation. Yeah, maybe like yeah, maybe it's too hard, right? Like it can't learn. Like math is just at this training stage at 10 billion tokens or something that it has seen just not possible to solve. And since the small LM output has less math in it, it's better. Yeah. Yeah. So some summaries about this. Yeah, we tested whether the results are within the noise, but we can pretty confidently rule this out. The student scale matters a lot, so we need bigger students to be able to differentiate between bigger generation models and smaller ones. Unfortunately, quality scores can't be used as proxies, also not diversity scores, even though GVandy helps for finding like good reasoning data. So there is unfortunately no substitute for training so far. And it looks like diversity is more important than polish, at least for the math example that we looked at. So this is it about the content part. Now it's about how we made this run. And here we're looking a bit at the infrastructure now. So each experiment rephrases 10 billion tokens. And as you've seen before, right, like if you choose the wrong model, it takes you a year of GPU compute. And also the serving setup makes a big difference, right? And since I ran this for 90 configurations, I wanted to make sure that I don't burn months of GPU time for nothing when I could have optimized it a bit more before, right? VLLM and SGLang already are like quite good at serving models fast, but still like configuring them correctly can make a huge difference. Leandro and Carlos from Hugginface had a challenge together with Google recently about serving Gemma really fast. And they had like a challenge with agents optimizing like throughput for Gemma. And I think they pushed it like fourfold within a few days with a few optimizations there. So there is quite a lot of potential here. I didn't go as far, but still there is quite a lot that can be done. How did we run this? We used data trough for generating the data at scale. So the way it works, we start with a Hugginface hub dataset. We have a reader, then a transformer, which is makes calls to like an inference engine like VLLM here. This also supports like more complicated rollouts, like where you have like a verifier inside as well, and then you reject certain outputs and so on. But here we just wanted to optimize for throughput, so we had the most simple setup possible. And then you write again to Hugginface dataset usually, right? You can run this locally or on a Slurm cluster as we did it for scaling it up then. So here we ran like a throughput sweep across different models. And we saw that for some models, you can speed them up quite a lot. For example, for smallLM2, 1.7 billion, the model used for generating the final fine phrase data set, we saw a 1.75x speed up in the end. So I had two tiers here. First, tweaking tensor parallel max num sequences and max num batch tokens. And then in tier 1 afterwards, the GPU memory utilization and speculative decoding. Different bottlenecks need different fixes. So for large models, they seem to be more memory bound. So if you add more tensor parallelism, even though the model fits on one GPU already, it adds to KV cache headroom, and you can fit more concurrent sequences, and that leads to a speed up. And for smaller models, this type of speculative decoding helped here, like n-gram and suffix, where you look at the inputs and then you just copy them over and like verify with the model how much of the input is correct. And for the small models, we saw quite an increase with that method there. So with the smallLM2, we arrived at 9,200 tokens per second per GPU in the end. And we also managed to optimize like GPT-OSS 120 billion to 6,000 tokens. So we could also have run that. It would not have taken it much longer. Yeah, you see there's like quite a big gain for each experiment in terms of GPU costs that can be saved. There's another visualization here, but viewed better in the blog post. We also added some convenience features for like automated updating of dataset cards that show you the progress of how the data is being generated, which can be helpful if you run it for multiple days or weeks. So finally, we arrive at the completed dataset. We used the smallLM2 1.7b instruct model that won the family ablation, and with speculative decoding, we arrived at 9,000 tokens per second. We used FineWeb Edu as a source dataset and used the 4 best prompts we had and ran it on 100 H100s in parallel. So we generate around 3.3 billion tokens per hour. So in total, we had 339 million documents, each rephrased 4 times with the different prompts. In the end, we arrived at 486 billion tokens rephrased. So on 100 GPUs, we get to 920,000 tokens per second. So 3.3 billion tokens per hour takes 612 GPU days in total. So around 6 days to really generate it if we had access to 100 GPUs at all times. And here are a few examples of the data set, but it's also better viewed in the blog post. Again, here to compare to the baselines with the different prompts. The table one is the best we found in this case, but the math is very close. and FAQ and tutorial are also still quite a bit better than the best synthetic baselines we compared to. We also compared a bit the cost per token to the peers, like Cosmopedia, for example, generated 2.5 million tokens per GPU hours, and Rewire only 1.1 million because they used a much bigger model and didn't optimize as much, maybe. So we used 24 times less compute, but generated more tokens. So to conclude, prompt design wins. It's by far the biggest lever. Structured prompts like table, math, FAQ, format, tutorial work quite well. Always mixing raw web data, just synthetic data alone loses on common sense tasks. 60 to 80% synthetic data work the best for us. Small models seem to be enough. 1B or 4B models seem to be good. If you're training like a bigger student model, then it makes sense to use bigger models for synthetic data generation. And diversity seems to be better than, or more important than polish at this scale. There's still many open questions. So for example, like, can you repeat data more often without performance loss if some of the repetitions are rephrased, right? So is the 60 to 80% optimum on what does it depend on, right? Like, is it does it change with larger student sizes or longer training? I fixed all the generation parameters. So what happens if we change temperature or others? Best of n filtering, we could generate multiple rollouts for each example and then have a verifier that scores and only keeps the best one, but obviously would be much more expensive again. Could use tools like prompt optimization to improve the rephrasing performance. I did that a bit, had negative results in the beginning. And longer pre-training. So far, I've trained for 21 billion tokens, so I don't have to generate too much synthetic data, and that I could have fast experimentation cycles. To what extent does it hold at longer scales? I did an initial experiment at the 100 billion token, and it held. So it was like pretty much the same ranking, which is good to see. But what happens if we scale to 1 trillion? I don't know. So we open source everything. The whole code, all prompt templates, evaluation details, fine phrase data sets, ablation data, generation framework, and all the results. Everything's open source. You'll find it and all the links in the paper or on the blog post. And here as well, happy to share the slides as well later. Thanks a lot.
That was awesome, man. Like this is great. Like it's so thorough. I mean, like all the different permutations that you've done, and then there's still so much to do. But then, like the fact that like you went and then you did all these ablations and all these different experiments, and you still kept everything kind of coherent and order. That's super cool. Like these are actually my favorite experiment because I don't know, you can ask so many questions back to back and still get a lot of insight. But then you can distill the stuff that matters afterward and then kind of sprawl more question, right? But like with a better ground that you're in. I still have like 2 questions. I think after that you have to go. Sorry for keeping you that long. Just like your general thought here about like this is for pre-training, right? What are you taught with like the usefulness of like synthetic data, but on the post-training side, right? Did you have early experiment or like taught around that already?
So I'm not really well versed in post-training, but like members of the team use synthetic data quite heavily for post-training. I think there was recent work called QED Nano that where they like generated lots of reasoning traces with big models and then fine-tuned the model there. And I think they were able to like match like Gemini 3's performance on math reasoning tasks like IMO. So yeah, I think you can like use it to distill knowledge from bigger models to smaller ones, for example.
Yeah, and my thought here is that like it would be very useful kind of data augmentation in an environment to have like this sort of like on the fly rephraser or like an indifferent like structure, but still kind of keep like the overall kind of problem set that you're using. So like it can make the problem easier a bit by like taking you step by step as a tutorial, or it can make the problem a bit harder by like asking it as like an actual problem, right? Or like handling it as a discussion. But then you distill it down to like not thinking too much about the format, but thinking about like the actual thing that you want the model to be training about, which is pretty cool. So, but to conclude, like, what's next on this direction for you, like on the field and stuff, like where you want to put and bring this next? I think you're trying to get the paper accepted at the conference, right?
Yeah, we got some good reviews, so I hope it will work out. Yeah, I think you had a really cool idea about making it multilingual, like basically find translations in reverse to generate a really big like pre-training data set for multilingual pre-training that could help like low resource languages a lot. I think that could be a very cool direction. At the moment, I'm working more a bit on harness engineering. So I helped out a bit on a project called Physics Intern that was about engineering a harness to solve physics problems much better. So we were able to push performance of Gemini from 17 to 30% just by using a different harness, which seems to make a huge difference. So quite excited about that work currently. But synthetic data also seems like a really cool direction, so might go back later.
Cool. And I mean, like everything is kind of connected. I was talking to Florian from Prime Intellect, and like I don't know, like the harnesses, like the evals, the benchmark, the environment, right? It's all roughly the same structure. It's just the infra behind that is a bit like it might be a bit different. But at the end of the day, it's just like trying to give the right format and data to the model so that they can just kind of learn or to evaluate them in like specific configuration. Really cool stuff, man. Thank you a lot for coming and and going through all my questions. That was super useful. I really appreciate it. So
Thanks so much
I'll
for having
be
me.
editing this out and then trying to put all of the links that you shared with us in the description.
Sounds great. Amazing questions. Was a lot of fun.
Have a great day.
Thanks. You too. Bye-bye.
Bye. And that's it. That's it for the pre-training synthetic data. Absolutely awesome. Like, you should really check out the book. I recommend, like, especially the blog post version, because there's a lot of like interactive stuff, and you can really explore the information. Really had a lot of fun on this. The paper also is great as a summary because they have so much content on this. He also has the slide available. So like well, from a philosophical perspective, I really like that like they did this experiment. They didn't have to, right? But then going so much in depth in this, and like being willing to kind of give to use the compute to kind of to test all of these different things. For me, it increased my understanding, my intuition, right? Understanding of like how synthetic data is helping, and how literally like pre-training is leveraging the data in order to kind of get to the final model. And still, there's so much more to do, right? Like so. Now, very bullish on this, and it kind of keeps into the the thread of like thinking hard about your data and like how you're presenting the data to the model and the capacity of the model and stuff. I think it's still, even to this day, like one of the most important thing you can do. You're understanding this very well leads to like very massive gains that you can get out of like whatever setup you have. Yeah, so that's it. I hope that you enjoyed, guys. Check out the stuff. I'll put everything in the description, and see each other next week. It's gonna be on Tuesday, and we're gonna check out the vector policy optimization algorithm, which is absolutely super interesting. So you can kind of read the paper this weekend, but basically what it is like a way to train the model to be having outputting more diversity of solutions. So then you can like put it into a harness that is like leveraging search, right? Like alpha evolve and stuff like that. Yep. So thank you all for the participation. That was great. I hope like all of your question was answered and you have a few more. All right. See you folks. Have a great day.